In this video, we're going to look at how we can apply encryption and hashing strategies to our applications for increased data security. So, I should have reset the headset before I started, but in this example, we're going to look at a sort of chopped down version of Project 5 that we did last year, which was our registering our users. Obviously, when we're registering our users, we want to pass the values into the database, but particularly things like passwords and maybe other personally identifiable information, we may want to obfuscate that so that people can't just get in and access everyone's details in our database. So we'll look at encryption and hashing. So encryption is a method of encoding or scrambling a message following a predictable pattern. I guess does make it that when someone just looks at the data, it doesn't make sense. However, because there is a pattern to it, if you understand what the pattern is, you can then reverse engineer it to get to the plain text. Hashing is a little bit more complex, and as such, it is considered to be undecryptable. So it's really great for things like passwords and stuff that we don't want people to be able to access. So we'll look at both, and for this we'll start by looking at encryption, and in particular a Caesar encryption. So because we want to use these sorts of methods in multiple situations, we will put them into an object library. The first one of which is a simple Caesar cipher or Caesar encryption, which is an example of a shift cipher, whereby we take all the characters and we shift them by a set amount. So just to save a little bit of time on this video, and not because I stuffed it up previously, but I've included the Caesar encryption in my Python library already. So we define the Caesar encryption. We have two inputs. So the input message that we want to encrypt and the key, which is the size of the shift that we want to make to each character. We then set up a sort of capture an output for the encrypted message, just started as a blank string, and then we'll add the letters as we calculate each one. And then for each letter in our input message, we go through, we identify the position of the letter using the ORD function. So the ORD function calculates the ASCII code of that particular letter. So for example, if we have an A, that's going to have an ASCII code of 97. B will have an ASCII code of 98, so on and so forth. So then to calculate the new position of the letter, we're going to take that position that we've worked out and we're going to do a little bit of maths. So the first thing we're going to do is we're going to take off 96, which basically takes that ASCII code of 97 for A and converts it to number 1. B will become a 2, so on and so forth. We then add the key. So the key is going to be a number which designates the shift size. So we're going to get the key. If it's 15, we're going to add 15 to our letter. So A plus 15 would be 16, which we can then convert to the letter P. After we've worked out that new position, we're going to do a bit of what we call modulus maths. So the percentage sign isn't used as a fraction of 100 in this case. It's used to do what's called modulus maths. And basically what it means is when we do a division of the two numbers, so in this case if we have the position after the shift and it works out to be 29, so we've already started at like U and we've got a shift of 8. I don't think that maths quite maths out. That'd be 29. So obviously there's no 29th letter in the alphabet. So we have to use the modulus to calculate what the remainder is when we divide it. So 29 divided by 26, 29 goes into 26 one time, and you have a remainder of 3. So basically it's getting it back around to say that, okay, the position of the new letter is position 3, which we know is letter C. Once we've worked out that position of the new letter, we just have to add the 96 back on to calculate it back to the actual ASCII code. So C would have an ASCII code of 99. Once we've got that new position, we then use the CHR function, short for character. So basically it's the opposite of the ORD function. So ORD works out the ASCII order of the letter. Character works out the actual character that sits in the position of that ASCII code we give it. Once we've got that, we can add that to our encrypted output. We go back and do the same thing for the next letter, until we've gone through the whole input message and we return the completed encrypted output. Alright, so we can actually run this in our app that we've already created. I'm just going to simply use the terminal for this one for output just to show you how it works, because ultimately we would want to store these values in a database rather than display the encrypted values on screen. So we'll just get, actually I can probably just do it straight, can't I? So the encrypted user is equal to, from the library we want the Caesar method for self.username.text. So we're taking the text out from the username text input to use as the input, and we'll do a shift of 15 just because I said 15 before. Alright, and then what we'll do, just so we can see it, is we'll print the encrypted user in the terminal. So we'll save the changes and we run the application. So you can see I've just got username, passwords, and the add user button. So if we say Fred and we hit run add user, you'll see nothing really happens here, but we get this message in the terminal of UGTS. So F with a shift of 15 becomes U, R with the shift of 15 goes like around the back of the alphabet, back through A, B, C, gets to G, E becomes T, D becomes S. So that's an example of a Caesar encryption. So yes, that's the first one, pretty simple, and again it's pretty easy to calculate the pattern because it's always the same shift. The next level up from that is probably what we call a Vigenère cipher, and that's where we change the size of the shift throughout the message so that it's a little bit harder to identify the pattern. And so for this we tend to use a keyword rather than a series of numbers, because keywords are easier to pass in messages and that sort of thing. So what we'll do is we'll go back to the library, and again, just to save a little bit of time, I don't encourage this behavior, but I will copy and paste because it does use the same sort of shift cipher base that we had with our Caesar cipher. So we've got our empty output to begin. We go through each letter, we shift, we work out the new letter, add it to the encrypted output. The difference is that we also need to identify the key letter as well within that keyword. So we're going to adjust this a little bit from what we've got. The first thing we're going to do is we're going to change our for loop to use a counted loop. So for I in range, and the range is equal to whatever the length of the input is, because we need to do it for every letter in the input. Alright, so now that we don't have letter, we need to change what we're looking for. So in this case, we're looking for the letter being input at index of I. So the first letter would be input 0, the next one would be input 1, so on and so forth. So the other difference is we do also need to identify the key letter. So to do that, so the key is now going to, actually, sorry, I shouldn't use key. I'll say key letter equals, actually, sorry, I've skipped a step. I need the key index first. So to work out what letter of the key we need to take the counter, and we're going to do a bit of modulus maths again. This time we're going to divide it by the length of the key. So if we're up to, say, index 6 of our message, and our key length is 4, so it's a 4-letter word, this will calculate that, okay, 6 divided by 4, we can divide once with a remainder of 2. So the key index we need is index 2. Once we have that key index, we can find the key position, which is the same idea as what we've done previously. We find the ord of key at that key index. Sorry, underscore index. Alright, and then one last little change is in the position. We had to sort of take off 96 to work out the numerical position of the letter in the alphabet. We do the same thing with the key. So key minus 96 will dictate the position of the key in the alphabet. So if the key letter is B, take off 96 to get to 2. Alright, so once we've made those changes, we can save that. I might can split it into 3, which is pretty handy, but probably not ideal. So I'm just going to get rid of the screens. We're done with the screens. It's all happening in here. Oh, so sorry, I've made one mistake. I need to change that to key position. So that little highlighting gave me a hint that I stuffed up, but I fixed it. Alright, so now we've got our Vigenère cipher. We can have a go at applying it. So I might just do the same thing. So Vigenère, so self.username.text, and I'll use the keyword of bird, so 4-letter word. So let's save, and we can run. So it all runs, which means that I've probably done it right, but we'll see once we press the button. So I might go with a slightly longer name just so we can try and pick out the pattern. When I hit OK, it has a little meltdown. So it's having a meltdown between, it's because I didn't save that change that I identified. So yeah, it does need to be key position. See how it was saying key? It's because I hadn't saved that change. So again, easy mistake to make. Happy to leave it in the video to show you that it's okay to make mistakes. Alright, so I'll try that again. Alright, so if we take Michael and we're going to iterate with the word bird. So M is position 13, B is position 2, so the shift size will be 2, which gets us to O. So M and then N and then O. I is in position 9. I is in position 9, just a coincidence. But that gets us to 18, which is R. C plus R becomes U. Alright, H and D becomes L. So then A goes back to the start, so B becomes C. Where am I up to? E plus I becomes N. And then R plus L goes all the way around the alphabet back to D. Alright, so we've now got our Vigenère cipher. I guess the great thing as well, once we've got these ciphers built in, we can stack them on top of each other. So what I might do is I'm just going to flip this around. So instead of I'm going to change this up a bit just so we can see the difference. So call that final encryption. Alright, and so what we're going to do is we're just going to pass this through. So we're going to, when we run our algorithm, we're going to first do a Vigenère encryption to encrypt the username. We're then going to take this value and pass it through a Caesar encryption to add a layer of complexity to our encryption. Because if someone just worked out the Vigenère pattern, they'd decrypt it and it still wouldn't 100% make sense. Alright, so once we've got this built, we can add in multiple layers of encryption to really scramble the message up and make it harder to decrypt. So I'm going to save that and give it a test run. Alright, so what we'll do is we'll do the same as before. So Michael, so we already know that when we have the word bird in the Vigenère encryption, it was O, R, so on. You can go back and look in the video if you don't believe me. So we should expect something different this time around. So when we add user, you'll see it changes now to DGJ. So as I said, M did become O, but then because we shifted it by 15, it became D. Alright, and so it goes around and around, and it gives us something that's a bit harder to decrypt again. Alright, so that's an example of our encryptions. But sometimes for things like passwords and that, we don't want to take a chance that they can be decrypted. So because that is a pattern, it is possible for people or even computer software to detect what's going on and to work out the username. So what we'll do is we'll look at hashing, which is essentially a one-way encryption. In that once you've encrypted it, it's almost impossible to decrypt. Alright, so as I said, we'll use this for passwords. So when we're completing a hash, we're going to use the MD5 hashing algorithm. So because these are quite complex, we can't recreate these ourselves. So we're going to borrow it from the hash library. So I'm just going to say hashlib at the top to import from the hash library. So no, it's called password one. So dot text. Sorry, print. Just completely had a brain fade there. So the hash is going to be generated by running the MD5 algorithm on our password that we enter. And then we're going to print the hash value for that. So if we run this, alright, so I'll do Michael again. We'll keep it nice and similar. And password, I'm just going to say password just for originality. Alright, and you can see when we run this, it creates a bit of an error. And it says type error, strings must be encoded before hashing. So when we run this, what we need to do is we need to add in the encode method. Alright, and so what encode does is basically takes whatever this value is and encodes it in the UTF-8 format, which is the default format for what we do. But with the way the MD5 algorithm is set, you do have to encode it. So we'll make that change, we'll rerun it. So we've got Michael, and again we'll use the word password. Alright, so you can see we've got a string for the encrypted username, but you can see now what we get is a MD5 hashlib hash object, blah, 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 blah. Which isn't very helpful because, we can't really store this object in a database. Alright, so the way around this is we're going to add in one more method. So once we've run the algorithm and on our encoded text, we're going to run another method called hex digest. And what this will do is turn this hash object into a string of hexadecimal characters. So generally this hex digest is used in a lot of hashing as a way of formatting these hashed values so that we can store them. So if I save this and run it, we'll have a look at what that looks like now. So once more, Michael is the user and the password is password. Alright, so now you can see we've got a string of characters for Michael, and we've got a string of hexadecimal numbers, albeit they are still characters, letters and numbers, for the password. Alright, and I suppose to try and highlight how hashing works, what I might do is I'll add an A for Michaela to just change the name up a bit. I'm going to add an A to the password as well. Alright, so you can see that the encryption will change a little bit for the username, but what we should find is the hash will change a lot for the password. So if I hit add user, you can see that, okay, if I change it to Michaela, it's all the same except now there's a T on the end. Right, so that gives me a clue that I was pretty close before with this to what that is. But what you'll notice is the hash has completely changed. It's not like it's 5, 4, or it's not like the 9 has changed to an A or a C or a 3. It's completely changed its name and number entirely. Alright, and I can even, even if I change it to another 8-letter word like password with a C instead of a D at the end, not that you can see that, but when I run it, again, it's a completely different outcome of hash values, or sorry, completely different set of hex values. So, this is why we use hashing, is it's so complex, there's no known way of decrypting it, so it makes it nice and safe. In saying that, we can make it even safer again, and that's by using a concept called salting. So if you think about salting as in, you've got your dinner and you're adding a bit of salt to it, it adjusts the flavor of the meal. It's the same thing with hashing, is if we add a bit of salt, because we saw if we change, one little thing in the password, it does make a massive shift to the hex value that we generate with the hashing algorithm. So another little tactic that we can use is salting our password before we hash it. So to do that, we're going to create another variable called salted. Alright, and for this, I'm going to keep it super simple. I'm going to take the text from password 1, and I'm literally going to add salt to it. So add SLAT. Alright, then when we go to hash it, we're going to add our salted password. We need to encode it, hex digest it. Alright, and then this will give us an even more secure password. So if we run this, I need to close the previous, run it again. So one last time, if we do Michael and password, I should have saved the original values, but I'm sure you'll work out it's different. So you can see Michael's still the same, but now the hex value starts with a B, which we didn't get before. So yeah, by adding salt to it, we've changed it up again to make it even harder for someone to access. Alright, so that's, I guess, the basics of encryption and hashing. There has been some challenges included there for you. Obviously, with these examples, I've only been dealing with lowercase letters. So you may want to look at how you can adjust this to handle uppercase, number, and symbol characters. Also creating the decryption algorithms, which is basically doing the reverse of what you've done to encrypt them. And then creating, I guess, a login validation page, which basically takes all your registered user information and can use it to verify their credentials. So I guess the hint with that one is that if you are using a hashing algorithm, you obviously can't use a decryption algorithm to work out what the username is, for example. You would have to actually run the entered password through the hashing algorithm and then compare it to what you've got stored. So you can't sort of decrypt the values in the database and then compare them. You have to actually run the encryption for the entered value and test it. Alright, I guess in terms of the encryption algorithms with the uppercase, numbers, symbols, I guess a little hint that I can give you for that, if I can get back to the library file, is previously here we've used the ASCII codes by using ORD. You do have the option of using the string library. So if we import string, alright, so you could say string dot ASCII letters dot index letter. So what this will do is identify in the it's dot ASCII, is it, sorry, I've got this wrong, ASCII dot lowercase no, that's not it either. Hang on, I'll just quickly Google it off screen. Oh, underscore, that's what I was doing wrong. Underscore lowercase, there we go. So what this will do is actually work out the position of the letter in the lowercase list. So then that way you don't necessarily need to muck around with the index there. So we'll save that. I'll just give it a quick test here to see if it's right or not. If not, I might just cut this out of the video. So Michael, we'll throw a password in there. Run. So it does give us a slightly different output. CFI. That's an interesting one. Oh, okay, I think I know why that is. Is because Michael, so is that right? M-I-C-H. So the H, when we add on the, was it 15? It shouldn't go too far, but I suppose it has. Oh, hang on, that's because I've also done the Vigenère cipher. I forgot about that bit. So I think what's happened there is because this is an index, there is a position 0. Previously we've been working on the scale of 1 to 26 as opposed to the scale of 0 to 25. So it doesn't matter where we do it, I don't think. I'm going to add it in here. If we add a position plus 1, I think that will work out better. So let's give that a run with that update. Michael, password. I shouldn't have put the tab in there because that's going to create drama. There we go. So we're back to what we started with, DGJ, So yeah, string lowercase. So that'll give you a bit of a clue about how to adjust it for things like uppercase letters, numbers, and symbols. Alright, we'll wrap the video up there. As I said, that's the basics of encryption and hashing, and time for you to have a go at applying that.